a break during Carnival, had some rest, jumped a little bit, a lot of rain, etc. Lots of rain. So after this break, we have this, let's say, the second half of Benedict's lectures. This is the fifth lecture. So he's going to teach Monday, Wednesday, Friday this week. And then the last lecture will be Monday next week, which actually we have to change some things because this room is going to be taken at 10:30, so we have to rearrange for that somehow. Okay? So yeah, so please go ahead, Benedict.
Okay.
And here is, if you want to just put your name.
Okay, so let me again start with a recap. It's especially important now.
Yes.
It's long ago, and there's been Carnival in between. So, okay, so the last thing I saw this last time was the topic of false vacuum decay. My goal is to kind of hopefully get through this today, or maybe in the first part of the next lecture, and then kind of the hard work is over, and we can finally talk about gravitational waves. But before we get there, so false vacuum decay, so kind of the idea is that we have a potential. And we are sitting here, yeah, as I said, in the universe, you can kind of like throw in corrections, kind of make this the absolute minimum of the potential, and so initially you sit here, then you fall down, and eventually a second minimum appears, but it's separated by the fifth minimum by barrier. And then the question is kind of, what is the tunneling rate, or equivalently also called the decay rate of this vacuum to kind of this vacuum. So this is called the false vacuum because its energy is higher than the one of the true vacuum which is here. Okay, so and then to get started, I first considered this in quantum mechanics, and at zero temperature. So in quantum mechanics, this would now be a potential for some particle. We'll call it x. And the particle initially sits here. And now the question is, what is kind of the tunneling or decay rate into this lower vacuum? And the formula I'm going to develop is a bit over the top for quantum mechanics. I mean, there you can just do it like in the way we all learned in quantum mechanics lectures to calculate the tunneling rate, but it will be then very easy to generalize from that to quantum field theory. So that's the yeah. So exactly. So I'll simplify quantum mechanics and I'll also simplify to temperature 0. So you can just imagine you have a potential like this at t equals 0. So and I say later what happens if I go to quantum field theory and to non-zero temperature. Okay, so then the starting point was kind of the path integral that we've already counted so many times during these lectures. So the transition rate from some position eigenstate xa to some position eigenstate xb is given by the time division of the Hamiltonian, and I can write this as a path integral. Feynman taught us with the boundary conditions that my path starts at time ta at xa and ends at time tb at xb. Phase proportional to the action. Okay, so then starting from this expression, we perform 3 steps. First we set xa equal xb equal x naught. So then we call this here x naught. This is kind of the state in the false vacuum, and call this x1. Okay, so first of all, I kind of restrict to these endpoints. So like my path needs to start in here. Then I'll do a big rotation once again. Real. And the last thing I do is I set tau a, so now the integral runs from, so I big rotate, and then the integral runs here from the boundaries are now given by tau a and tau b, and I'll just say that tau a is minus some value tau hat over 2, and tau b is plus tau hat over 2. It's just a useful parameterization. Okay, so once I do this, what I get is the following expression. So now I'm just doing mathematics, right? I'm just, the physics behind this is not yet clear, but it'll be clear in a few moments actually. So I'm just performing these steps, and that's what we already did last time. I don't know if you remember that. So this becomes e to the minus h tau hat, going from x naught to x naught. And here, what appears is the Euclidean action. So the Euclidean action for one particle. Euclidean action appears because I big rotated, right? So I don't know if you can still read what I'm writing here. In principle, all these formulas have been on the blackboard last time already. So this is kind of this is the action, and then when I rotate, I change the sign of this kinetic term here, and it becomes the Euclidean action. Okay, and now we took the limit of this parameter tau hat going to infinity, or to some very large number. And then last time I showed that, so if you kind of expand this into energy eigenfunctions, then you, taking this limit, projects onto the lowest energy eigenstate. Or here, the exponential lowest energy eigenvalue, because that's the smallest, so it's exponential decays the slowest. Expand in energy eigenstates, and what I find is that this goes to e to the minus the ground state. This is for large tau, right? I mean, for finite tau 0, for large tau, I'm taking the limit, times some wave function, where psi naught here is the lowest energy eigenstate with energy E naught. Okay, and then from this, we found that, so now we can take from this formula, I can extract the energy in the following way. infinity, 1 over tau hat, log of this expression. So that was kind of the last result we derived last time. So you take this, you take the log, which projects as this, and then you divide by tau hat, it takes a little bit tau hat to infinity, and then you just project on the energy axis. So this is a way to extract the energy eigenstate, the lowest energy eigenstate, and then another formula I derived last time, which I will not rederive now, is let's assume this energy has an imaginary eigenvalue, or has an imaginary component, and as I showed last time, the decay rate is given by -2 times the imaginary particles. Okay, so kind of the strategy is now, so now we know we know how to get the energy eigenvalue. Let's assume it has an imaginary value, then we get the decay rate. So now, in order to evaluate this, we kind of have to do the same steps on the right-hand side. So this was the left-hand side. Now we want to do the same steps on the right-hand side. Well, sorry, no, we want to exactly. So, well, okay. So now we have to evaluate the right-hand side of this expression. Okay. Any questions so far, or? So now, the idea is now to expand the right-hand side here around the stationary points of the Euclidean action. So ideally, I will later say this is not actually, well, okay, ideally this would be a minimum of the action. So if I expand around the minimum of the action, then kind of away from the minimum, the action grows, and the exponential decays. So the contribution at the minimum is really the dominant one, right? So this is kind of what you do with sparse integrals, which you have seen this already before. So we do the same thing. So so now let's expand. So next step is next expand the right-hand side of this relation here around stationary points of the Euclidean action. And the stationary points of the Euclidean action are just given using the Lagrange equations. The relation that I have to solve for. So we're looking for, I mean, this is a path integral, right? So we're looking for paths, like, which means these are functions of tau that start and end at x naught. These are our paths, right? We look at a function, such a function for which the Euclidean action has a stationary point. Because, well, at least if it's a minimum, again, if it's a minimum, it's clear that this will use the dominant contribution. As we will see later, well, we actually have a settle point, but certain subtleties that I will discuss later in more detail. Okay, so, and again, so then the Lagrange equations tell us that a path for which the Euclidean action is stationary. It is given by just solving the equation of motion. And we had this equation, and then we have the boundary condition. The path ends at starts and ends at x0. And I haven't taken the limit till I have to infinity. Okay. Okay, now if you can remember classical mechanics, so you will recognize that this is just the equation of motion of a classical particle moving in a potential minus d of x, so an inverted potential. So let me just depict what we've done. So we kind of started with a original problem where I want to determine like the tunneling rate. And now by expanding around the stationary point, what we simplify this to is it's the motion of a classical particle in a potential that goes like minus e of x. So this would be, so I'm just inverting this now. Right? This is x0, and this is x1. And we're kind of looking for the motion of a classical particle in such a way that it starts here at initial terms, then it does something, and then at the final time it ends again at x0. And that's a very important step, so I should stress it. So we started with a tunneling problem, a quantum mechanical problem, and now we ended up with a classical problem that we have to solve. That's not the whole. That's not everything we have to solve, there's more to do, but that's kind of the most important part of the problem, it turns out.
So it's funny that there's no information about x1, the other minimum, right? Up to now.
Well, so in quantum mechanics, I think you just tunnel to this point here, right? So it doesn't actually matter. In quantum field theory, it's the same, so you don't actually have a dependence on x1. It will depend on the, so in quantum field theory you can kind of tunnel to, you don't tunnel necessarily to the point with the same energy, you can tunnel to a different point, but it can, because we'll be far away from the absolute minimum. So
at some point the width of the size of the tunneling matter.
Sorry?
The size of the tunneling length to matter. Right?
Sorry, no, it
It will matter at some point.
the matter?
No, it will at some point it will be important. Be relevant. The size of the shape of the potential.
Exactly. So what's more important is the shape of the potential. So kind of this part, not so much this part, but it's this part is important. Exactly. So, which you can already see. Well, okay, you cannot really see it yet. So you will see in a few minutes how this plays out. Okay. So we do this. Okay, let me keep this expression here. So we'll use this part. Here it is now. Okay, so again, just to make clear what we're doing, right? So we know how to evaluate the energy, the lowest energy state from this side, and if it has a magnitude part, you know how to determine the decay rate, right? So now, because they're equal, what we want to do is that we want to evaluate the right-hand side. And the way we do this is we expand around the path integral around the stationary points of the Euclidean action. So, okay, let me just, so this is of course not everything, so we solve this, and we find, so let's call the solution to this x bar of tau. And I will discuss some possible solutions in a few moments. But for now, let's just assume there's such a solution. So now we can write the Euclidean action that appears here as, so we expand around this path. So we write a given path that we integrate over in the path integral, x of tau as x bar of tau. That's a solution to this equation of motion, plus some fluctuation. Okay, and now what I do is I just plug this expression here in the Euclidean action and expand. So let me just do this. So, okay, the leading order term is just SE of x bar, right? So if I plug this in, I get one contribution definitely goes like x bar. Okay, and then the next is a priori. Now I can expand to linear order in Z. So let me do this. So now to linear order in Z, I get, so I plug this expression here in and square. Then I get dx bar, d tau, dz, d tau, plus d prime of x bar, z. These are still functions of, no, sorry, what am I doing? So this, exactly, these are functions of, I have to integrate from minus tau hat. There's a contribution to linear order, and then there's a contribution to quadratic order. Again. So now I get this squared dz d tau squared plus d prime prime of the stationary point times z squared of tau. And that's a factor 1/2 here from the tail expansion. Okay. Okay, so now I can modify this slightly. So I can partially integrate. So partially integrating, this becomes minus d squared. So what I've used here is that z is a fluctuation around this path here. This path already satisfies the right initial and final conditions. So at tau equal minus tau hat over 2 and tau equal tau hat over 2, this is equal to x naught, meaning that at the boundaries z has to vanish. So this means that, okay, this was kind of crucial in me being able to partially integrate here. So because the boundary term is this, is a total derivative of this, with this evaluated at the boundaries, but this vanishes, right? So, okay. And now you see that so this is just minus d squared. So this is just really, if you look at this is just this equation of motion here. So So telling you that the expansion to linear order that vanishes. Right? And just use the equation version. And this is just a statement. I mean, this is of course what you should get, right? Because I'm looking for a stationary point, so the linear term should vanish. So okay, so let me get this. And here I can also partially integrate, just a bit more convenient. So I write this as minus z of tau d2 z. I just partially integrate. Again, use the fact that at the boundary this vanishes, so the boundary vanishes. Okay. So then I can write this as, sorry, or rather I can write this as S of x bar, the stationary point, plus 1/2 the integral of time tau. Now I write this way. Okay, and now this can be written in a fancy way. This can be interpreted as the determinant of this operator here. I don't know if you probably have seen this already in one of your three lectures. If not, it doesn't matter. In the end, I will not actually really evaluate this expression. So we can just use this as a shorthand notation for this side. So we write this as 1/2 determinant of this operator.
So it's not the path integral of that gives the determinant.
Sorry?
This is not the path integral of that term that gives the determinant.
No, but it's a plus. I mean, it is.
You are going to plug this into the path integral.
I mean, exactly. So it is a path integral. So, sorry, you're right. So, sorry, what I'm saying is not correct. Exactly. Okay, let me erase this here. You're right. Saying it's not correct. I have to first plug it into the path integral.
That would be the trace, right?
Hmm?
That would be the trace, right?
I guess. Yeah, I guess you can call it the trace, yeah. Exactly. Yeah. Exactly, sorry. So, very good point. So, what I have to do now is I have to plug this in here. So, this is very easy. E minus S. E. And now, okay, so now I write this, so I can now use this. And now there's, I mean, okay, I didn't write so there are terms of order Z cubed when we get into it. So this I can pull out. This just goes, just a factor S of the stationary point. And now, exactly, and now I plug this in, so I get some boundary conditions, and we write them now. E to the minus space. Exactly. And so yeah, actually now the logic is also a little bit clearer. So what you can think of this is kind of you expand these fluctuations around the stationary point into eigenfunctions of this operator. So then you essentially get a sum over squares over the eigenvalues here. Yeah, then you can perform the integral as a Gaussian integral, and then you can see that this is written, this can be understood as the determinant of the operator. I don't want to delve into this too much because again we will not actually evaluate it, so you can just think of this as a shorthand notation of write this as in general normalization integral. I write this as the determinant of this operator. Any questions?
Path integrals over Z, right? And the integral is from 0 to 0. So
Exactly, sorry. I should probably change the. Yeah, so I should actually make like this. Exactly. So we continue now. Let's continue here. Okay, so now let me discuss some example paths. So it becomes a little bit complicated. So again, we're looking at a classical particle moving in the inverted potential. So starting here and ending here. And the simplest path you can imagine is just that the particle sits at this point. I mean, it's a classical particle, right? So if you just put it exactly on top, it will just stay there forever. So the simplest path. Solution to the equation of motion that I just erased would be x bar of tau equal n of x naught, independent of tau. So just sits here forever. Okay, and now this I will not actually do, but you can show for large in the limit of large tau hat for large times, then this integral, you can evaluate this determinant. To get this. This is expression that if you evaluate, if you work really hard, then what you find is following expression. Where omega is the second derivative of the potential evaluated at x naught. now I can, so what I need to do now, I want to kind of evaluate this expression to extract the energy eigenvalue from this. So I've written it in this form now. I know now what this determinant is, so the last thing I have to determine is kind of this factor here, but this is very simple. So as e of x bar, and this is just a constant, right? So just do it explicitly. Guess what will happen? So there's a constant, so this is 0. And this here, I can also just choose to be 0. It actually doesn't matter. I'll show you in a second what happens if it isn't 0, but let's for the moment assume that it's 0. So then this factor will appears. This factor here is just 1, right? So what I get is that I get, okay, let me equate this to the left hand side. So we have this 2 minus h hat x naught. Now I use that this is equal to this, and this is equal to this. This is 1, and this I just evaluated. So what I get is that this is equal to the minus and this is okay, now we had our master formula, how to extract the lowest energy eigenstate from this formula. So we just take the limit. Okay, let me just write it again. So this was E naught is equal to minus the limit of tau hat going to infinity, 1 over tau hat of the log of this expression. Okay? So now I plug this in here and take this limit. And what do I find? I find that this is omega over 2. And that should be familiar to you. Because this is just, so the original definition like this. This is just the energy of a state localized at x naught, where I approximate the potential where it's quadratic piece. And then this is just the ground state of a harmonic oscillator. So it was a very complicated way to obtain a known result. Right? So you can say, okay, why, what the hell?
So where is the 0 point? Where is the 0 point energy?
Hmm?
Where is the 0 point?
So yeah, exactly. So sorry, so I set the 0 point energy here to 0. Right?
Okay.
So if I don't, then you see that it just shifts by this. So. Because
plus the hat.
because the e to the
This one.
so this just goes to v over. So exactly, I could have also maybe would have better. This goes to minus v of it's not tau hat, right? Because I integrate over tau hat over tau,
Yeah.
and then you see that this just shifts it to it's not here. Okay.
So it's real, does not decay.
Exactly. So one thing that you learn is that it works. It gives kind of what you would expect, but yeah, it's real, so it doesn't decay, which is kind of like, well, you're just looking at the ground state energy a bit. So now we have to look at a different class. And so one natural guess is that because we want to kind of, if the field tunnels, kind of probes this region of the potential. So the natural guess is to look at a path that also kind of probes this region of the potential. Now inverted. So it's a path that kind of starts here, rolls down, gets to this turning point here, let's call this XB, and then rolls back again. So it goes like this. That is the next path we need to look at. And so now you can wonder why, I have to end up at, so I have to start exactly here at initial times and end again exactly here at initial times. Why do I even roll down? Right? But now remember that we take the limit of we take an infinitely large time interval. So now you can think of the limiting case where you start, okay, you first start here, right? You roll down and roll back. Now you make the time interval a bit larger and you go a bit closer to the hill. Okay? And then whenever you make the time interval larger, you go a little bit closer to the hill, and as a limiting case, you can get the situation where at t minus infinity, you really start on top of the hill, and then the field slowly gains velocity. At some point it rolls back, and then at t plus infinity, it again ends up at the top of the hill with zero velocity. So let me draw this path. So I'll reverse this now. Remember this expression? So what we have now? Yes.
From this picture, the classical picture, the probability of it settling at the minima seems to be larger, right? And rolling back.
Sorry, say again?
The probability of it to settle at the minima, which was maximum over there, seems larger.
To settle at the minimum. So I'm looking, my boundary conditions are really trajectories which start and end at this point. This is just my. So of course, if you can have any types of. If you have a particle moving in this potential, of course, if you put it here, then their path where it just will oscillate around this minimum, for example, right? Or there's a path where it just goes down here, for example. These are all not the paths we're interested in. So the path we're interested in is really which satisfy boundary conditions, and the boundary conditions are that at the initial and final times, the particle is here on top of the hill. Okay? So this was a simple, so now more interesting. Stationary point. More interesting solution to the equation of motion with random conditions. Let me draw this as. So this is now x as a function of tau. And as I said, so I'm looking at the case where at t minus infinity, I'm sitting here on top of the hill. And then it rolls down, gets to this turning point, rolls back, and ends up again at the top of the hill. And this really makes, of course, this only makes sense in the limit where I send the boundaries to infinity. Right? Then I can take this limiting case that at t minus infinity it starts here with zero velocity, and at t plus infinity it ends again with zero velocity. So the path looks like this. For most of the time, the particle sits here on top of the hill. So this here is x naught. And then at some point, it gains velocity, it rolls down, turns, rolls back, and again sits here for most of the rest of eternity. And so this is kind of, so it starts here at x naught, then at some point, let's call this tau c, around some point tau c, it rolls, it reaches this turning point here, you know, the xb, it rolls back, and then again, it, to a very good approximation, just sits at the top of the hill for the rest of eternity. And this is an example of a so-called instanton. And the name is kind of natural to guess why the name was chosen, because it's something that like happens at an instant in time, right? So yeah, suddenly something happens and then nothing happens anymore. So it's an example of an instanton, and it has a more specific name. It is called the bounce. So-called bounce. And that is because it rolls, bounces off here, and rolls back. Right? So, okay, and you can check that there are solutions like this in the equations of motion with a given boundary conditions. Okay, so let's assume we have such a solution. So let's call this, bounce solution again x bar of tau. So some function that now we have to solve the equations of motion for, but as I said, it can be done. And now let's evaluate integral. So now, so this is a stationary point of the path integral because it's also the equation of motion. So now we get a contribution from one such solution. And let me write this. So contribution to path integral from one path. And as you can guess, we will generalize this momentarily. So now we just look at one path. Again, the expression we have to evaluate is this monster here. Boundary conditions. Okay, and let me introduce abbreviation that will be useful. So I call the Euclidean action evaluated for this bound solution E. And again, so you can solve the equations of motion for this, and you integrate it, you can calculate this. So straightforward process. So let me call this P. And now, so I can write this as, so remember, I now expand the path around the stationary point. So I get a contribution that goes like e to the minus s of this. And again, we call this b. And now I get a functional determinant. Again, the same way we did before. Now let me write this functional determinant in a slightly involved way. So I write it as, it's a good guess would be that because the path sits at x0 for most of its time, this is kind of a reasonable first guess for what we'll get for the function determinant. This is the same function determinant that I had before for the case where the path is really just restricted to x0. So this is again this quantity here, omega over pi, and that's the second derivative evaluated at x0, e to minus omega. And I can think of this as some kind of correction factor taking into account the fact that kind of like here something happens, right, that deviates from being started at okay, and a natural guess, I will just put this out here, it will not matter so much, I just wanted to be sure that you kind of see the expressions that are used in the literature, but since we don't really evaluate it, so a natural guess would be that k equal determinant. So actually the determinant expanded around the bound solution. And then divided by this expression here because this is what I can use. Natural guess, but as I will say later, only almost true. So we get something that looks very similar, but not exactly like this. Okay, so this was this is the path integral evaluated for one bound. But now, again, this sits here like for almost eternity, right? And then suddenly does something, and then sits there again for a long time. So now in principle, I could have a solution where like I have this happening twice. So nothing happens, then it kind of does this, it goes back to x0, almost, then it does this again, and so on and so forth. So I can have superpositions of bounces. I can have n bounces at the same time. Now we have to evaluate the path integral for the case of n bounces. This is a step in the it's a path integral, right? So I integrate over everything that can happen, and if I can have paths where I have n times this bounds, then I have to include this in my path integral. So let's estimate the contribution to the path integral from an n bounds configuration, and I will assume that. So we assume that the bounces are widely separated. So meaning like you can have a situation like this, where it's again, and so on and so forth. So they're widely separated in the sense that they don't overlap, right? So they're clearly distinguished. Intermediate terms, the particle sits to a very good approximation in x naught, and then it starts to bounce again. Okay, so we assume that they're widely separated, and the centers located at times and A with tau 1 to tau n. So these are kind of these times where around which this movement is centered. Right? So, and this goes under the name of dilute gas approximation. And I will say in a few moments why this is justified, or in which limit this is justified. But for now, let's just assume this. Okay, so then again, the Gauss integral. So for one bounce, this is what I got. Now for n bounces, what I will get is just this to the n, but not this to the n, because this kind of takes into account the intermediate time intervals where I'm sitting at x naught to a very high precision. So you can work this out in a little bit more detail, but I will not have time to do this now, and then you will find that this is kind of what you get, but I think it's intuitively clear. So you kind of get this to the nth power because you have n bounces, but this only appears once because it kind of counts the almost eternal time during which the particle sits at x naught and nothing happens. So it's kind of the time that occurs before. So what I get is e to the minus b times n, this correction factor to the n, and then let me just write this. So this was kind of the contribution from particle sitting at x naught, and evaluate this. Any questions? Or? Okay, so the next step is now, so I assumed that they're localized at these times here, but if you look at this expression, the centers doesn't appear here, right? So it's independent of that. Yeah, so okay, but now I have to take into account that these centers can be everywhere along the time direction, right? So I can move them around. And this I take into account by integrating over these time variables. And I integrate in a way that I kind of keep this order. So the next step is now integrate. Integrate in a way that does not change the order. So the first center is allowed to be anywhere between minus tau hat over 2 and tau hat over 2. And then of course it's always understood that later I will send this to infinity, right? Now tau 2, because it has to be smaller, I have to integrate only from, sorry, I did write the wrong expression here, so I have to so like this interface, right? So now tau 2, the center of the second bounce must be kind of happen after tau 1, so I start the integral at tau 1. Okay, and then it goes like this. And the last integral is just from tau n minus 1 to tau n over 2 tau n. Okay, now you can just work this out and just simplify it in a very nice way. It gives tau to the n, tau hat to the n, so the boundaries over n factorial. Okay, and now the fourth step is, so we've now taken into account the possibility of the n-bounce configuration. We've included the possibility that, taking into account that they can be kind of localized along arbitrary points along the time direction. And now we just have to sum over all n-bounce configurations. So sum over n is the last step. So then we get kind of at the total contribution to the Paris integral. Boundary conditions here. Okay, now I'll combine everything. So I get, okay, there's this factor, this one here, I pull out because it's independent of everything, it's just a constant. So omega over pi. Out. And now I sum over all n-bounce configuration, including the possibility that there's no bounds at all, so n equals 0. Yes?
I didn't get why the upper limit of the integral is always tau over 2. I didn't get why the upper limit of the integral is always tau over 2.
So because I just want to move these centers around while keeping this order, right? So tau 1 can be, tau 1 is my first, so I just integrate over tau 1. Tau 1 can be anywhere between minus tau hat over 2 and tau hat over 2.
Ah, okay.
So now tau 2 must be larger, right? So it must be larger than tau 1, but it can again be anywhere between, now it can be anywhere between tau 1 and tau hat over 2, and so on for the other.
I mean, maybe it's just inverse because there tau n is the greatest of latest.
Sorry? Ah, sorry. Did I do it?
Yeah.
Ah, yeah, sorry. Okay, I see. Sorry.
Yeah.
Yeah, you can either change the boundaries there or here. Sorry. It doesn't matter, right? So you always get this factor till head to the end of that factor. Yes, you're right. Okay. Okay, so I now sum this over n from 0 to infinity, so I get this factor here. I'll add to the n over n factorial. And I get this factor from the nth bounds into minus bn k to the space. Okay, and then from this I get, okay, I want to write this again, the third here is equal to omega pi. Sorry, I think it's over 2. I'm not sure why I'm writing this down. It's over 2, right? I think it doesn't matter, this drops out anyway. So, okay, let's write omega over 2. 2. And, okay, and this here just gives the exponential function. So, this is minus tau hat 1 over 2 minus k e to the minus b. Okay, now we're almost there. So now I plug this into this master formula for the lowest energy eigenstate. I take the limit of tau hat going to infinity, and then you see that I just project onto this piece here. So then from this I find that the lowest energy eigenvalue as estimated from this. The bounce configurations is omega over 2 minus k okay, now I can quickly justify the gas approximation. So
sorry, Benedict, I'm a bit confused. So you have one exponent of e to the dot omega tau over 2, and then e to the minus tau.
sorry, this is wrong. Yeah. So exactly, this is already included here.
This is already there.
Yeah, this is already included. Okay, so now we can just quickly justify the new gas approximation that I made. Maybe the point is that kind of if you have a sum like this here, and then you have this a sum like this. I just write, let's write y to confusing. We have so many axes here, so y to the n, 1 over n factorial. This just gives the sum of this type, but this gives the exponential function. And this is dominated by terms in the sum with and less than. Sorry, I just have to think for a second, so I'm not sure. Yeah, so it's just dominated by terms like this. And this and this you can just plot the functions, you can see that. So that these are the terms that kind of give the dominant contribution to this sum. So then, if I plug this expression here in, and this is, so this sum here now is dominated by terms with k tau hat e to the minus b, terms with n less than tau hat k e to the minus b. And now I can write this as this. And now remember that this is kind of the total time interval I'm considering, right? So this is kind of the density of bounces in time, right? And you see that the density of bounces, so the sum is dominated by terms for which the density of bounces is exponentially suppressed. That's kind of the main point here. So I can kind of, for b much larger than 1, I can kind of take the limit where the dilute gas approximation is definitely justified. I mean, now I can work a bit harder, I can kind of compare. So essentially what I want to compare this with is, so again, so the sum is denoted by terms for which the density in time of bounces is less than this. And now I have to kind of, so each bounce comes with like a certain width in time that I can determine from solving the equation of motion. And well, now if I really want to check this, I kind of have to evaluate this determinant or estimate this determinant and kind of check if this is a good approximation. But I mean, the main point is that there's a clear limit for which this is justified, right? So for B image larger than 1, if we go to the limit of large B, the dilute gas approximation is definitely justified. Okay, so now comes a slightly difficult point that I will just briefly mention. Don't have enough time to discuss this in detail. So the point is there are two problems with K. So remember, I don't have this. More, but we kind of expected that K roughly should be something like determinant of divided by determinant for the case that the path just sits at x0. Okay, and yeah, let me just throw this out. I mean, I don't really have time to discuss this in the detail that would be necessary to really appreciate it. So let me just mention this to you, and then if you're interested, you should probably just go to the literature and have a look. In the end, I will never really evaluate this expression anyway, so but I think it's good to know that there are kind of these like difficulties. I mean, you will see this if you look at the literature, it's discussed there at length. So one point is that the operator this operator has a zero eigenvalue. So again, the idea of evaluating this determinant was we kind of expand, we have this Gaussian integral, we expand this operator into its eigenfunctions, and then we kind of can write this expression as a product of the eigenvalues. But now one eigenvalue is 0, and that causes this expression to diverge. It turns out, so this 0 eigenvalue is really just the fact that kind of so the bounds look like this, right? And as I said, we can consider configurations where it moves the center of the bounds around the time direction. So this, you can see this costs no energy in the path integral like this direction. If I change the bounds configurations by moving around the center of the bounds, there's no cost in energy in doing that, and that exactly corresponds to the zero eigenvalue. But this is actually something that we have already taken into account, because we have this integral here. This integral is exactly what takes this already into account. So what you have to do is you have to exclude the zero eigenvalue from this determinant. Include it, And then what you get is this, because this is what appears in K, and this is modified to, so you denote this with a prime, so you write this as determinant prime. And you get a factor of B to the power. So this notation is not a derivative. I mean, this means that 0 eigenvalue is excluded in evaluating the determinant. Again, I mean, so my main point was that kind of if you see this notation in the literature, so you have a rough idea of what it means. Since we will not actually evaluate this, it is not so important after all in the end. The more important point is that the operator, again, this guy here, has a negative eigenvalue. And this means that at face value, this expression just blows up. I mean, this is really badly defined. And this negative eigenvalue has to do with the fact that we are looking at a state that is unstable. So that's kind of about to decay into another vacuum. Okay, and here I will be very brief because this would take, I guess, probably another lecture to properly explain this. So what you kind of have to do with this, to make sense of this expression, or of this expression, you have to analytically deform your path into the complex plane. So there's a procedure that allows you to kind of make sense of this expression in the presence of a negative eigenvalue. And that continuation into the complex plane of the path is what gives you an imaginary part of this object here. And remember, the imaginary part, so the imaginary part of K means the energy has an imaginary part, and so K. Okay, so again, I apologize, but this is...
So that's not a problem. That's the origin.
That's actually, it's at face value first a problem, but then in the end, it's kind of what gives you the, exactly, it gives you
K.
it gives you the K, exactly. So let me just, so if you're interested, so if you are not scared, then let me tell you. So you should first have a look and just give you some homework now. So you first should read section 2 of Callahan and Coleman. That's a reference I gave at the beginning. That's a paper that this whole discussion is based on. And also, if you're interested, so I'm really following this paper. Almost one-to-one. So this was, just so that you find it more easily, this is called Fate of the Phase 4 Vacuum. Fate of the 4th vacuum. It's very brief, so the discussion is actually surprisingly brief. It's just half a page. Well, or even, not even less, so 2 or 3 paragraphs. So I didn't find it very illuminating. But it's a very nice discussion in a relatively recent paper by Matthew Schwartz and collaborators. This is Schwartz who wrote this nice QFT book. Also, this paper 16, so this is the archive 1604 over 6090 in section 3. And he goes in a lot of detail, like through this procedure of like why you have a negative eigenvalue, how you have to perform this analytic continuation, and then how you conclude that there is a measurement part. For us, it is enough to know that there is an imaginary part. So what we find is perform this analytic continuation. And then we find that this object K picks up an imaginary part. We can just write it. So this is kind of from taking up the zero eigenvalue. So I get the B, yeah, and then essentially the new point is that there's a factor 1/2. Okay, so now we are almost done with computers. I don't know how much time this will. Okay, so now we know that this object is a measuring part. We know how to look at the K rate is just given by the imaginary part of the energy. So from this we can now conclude that the K rate is given by this is our master formula. So again, B is the Euclidean action for this bound solution, right? So that you just, I mean, for some cases there are analytical solutions, but in general you just solve it numerically. You solve the equation of motion numerically with the boundary conditions, then you plug it into the Euclidean action, and you can get B. Okay, and now you have this ugly object, the determinant, but kind of the point is that the B is much more important because the B enters exponentially, right? So what really sets the overall order of magnitude of the decay rate is this B, and the B is easy to calculate. This object here is difficult to calculate, but it is less important. So so in quantum mechanics, we are still in quantum mechanics here, right? In quantum mechanics, I think you can actually evaluate this in closed form. Maybe it depends on the potential, I'm not sure. Probably with simple potentials at least. In quantum field theory, this is at least very, very difficult or even impossible. So, so later you will see a similar expression. We will never evaluate this object, we will just make a order of magnitude estimate of this object. So, because again, the more important thing is here that each of the modes be fair. Okay, let me maybe, can I? Yeah, 5 minutes? Or let me just quickly start with the generalization of quantum mechanics and quantum field theory. Again, so So in quantum mechanics, you can calculate the tunneling rate in a much simpler way, right? But the reason why we went through all this pain was to write this formula was that now this can be generalized quite straightforwardly to quantum physics. So let me just start this up. So organization Q of t. So again, the starting point now in Q of t is again the path integral. So there's an expression that we also already had in the blackboard a few times during these lectures. So this is the transition amplitude of some field configuration phi A at time Ta, which is some field configuration phi B at time Tb, and this integral is the path integral where the boundary condition is phi of Ta x is equal to phi A of x and phi of B is B of x and e to the action. Okay, and now you can do the same steps as before. You identify these points, you Wick rotate, and make a median choice for the initial and final time, so you go through the same steps. And almost everything goes through, and you get a formula that looks. So then you expand around the stationary points, right? And then you get a formula that looks like this. So, just write this now. So you can get this again. Ideal expression is functional determinant. Now it also depends on the spatial derivatives. Box around it to make clear that it's a very important result. Let me explain a little bit more the expressions that appear here. So this is now, so this was a decay rate, this was in quantum mechanics, this was a decay rate, so a rate per time, decays per time. In quantum field theory, what you get is, you get a decay rate per unit time and unit volume. So this is decay rate per unit time and volume. This is the action, the Euclidean action of the bound solution. And I will tell you probably next time how to calculate this. But again, it will be calculated by solving a classical equation of motion. Again, you can think of it as a particle moving around a potential. The equation of motion will be slightly different, but the main point is again a classical equation of motion that you solve here is quite the solution to the Euclidean action. So the Euclidean action now is for, so we're just doing for the scalar field, right? So this is just the usual expression. So so this is here, phi bar is kind of what I will, so phi bar is, that's really the bound solution. I will tell you next time how to evaluate it. And phi naught is my notation for the minimum, the false minimum. So potential like this. Call this qualitative format. It's more or less straightforward here, the generalization of the expression. Okay, and I think this is a good time to stop. So next time, we're almost through with this. So next time we'll just tell you how to evaluate this quantity B, and then we are ready to calculate the covariance. Okay.
Thank you. Questions for Benedict? Oh, I think it was crystal clear.
I hope so. I mean, otherwise.
The analytical continuation is made in what variable?
So yeah, so you can. I mean, you can. Well, essentially, there's one direction that you understand where the instability comes from. The negative eigenvalue will be. So exactly. So you can boil it down to one variable, and then. So I mean, a path integral in general is like about infinite variables, right? Integral about infinite variables. But this analytic continuation you can boil down to one direction.
Like in the QFT case, is it continuation of some coordinate of the field itself?
No, it's really like it's an analytic continuation of the path integral. So let's say you integrate over functions that of tau or something. So you can expand this into eigenfunctions. So what of tau is